let us do the first way to do the hydration of an alkyne. So this is going to involve some steps that are going to involve doing a tautomerization. So tautomerization is a shuffling around of pi bonds and hydrogens, and we see it between enols and ketones and aldehydes. So we can get this enol keto tautomerization. And so for this, what we're going to do is we're going to talk through one of the 3 ways of doing this hydration that we're going to learn in Organic Chemistry 1. And each of the subsequent videos are going to have different versions of these. So the first one, we're going to do the simplest hydration, which is using an acid. So for this, I'm going to take an alkyne, and I'm actually going to show you the mechanism, and then we're going to look at the 2 possibility of products depending on when I do the terminal versus internal alkyne. And you'll see the only one that we have to really be careful of is the anti-Markovnikov one. If I do the regular acid or oxymercuration, I am going to basically only get ketones. However, they may be a little bit different of a ketone depending on what you have. So let's take a look. Let's get into it. So let's start with the hydration of an alkyne, and we're just going to generically do a mechanism, and then we're going to talk about the products, and then there will be 2 other videos with the other mechanisms. So I'm going to start with an acid, and again, this is very much like the alkenes. That's why we cover them together between the 2 chapters, except this I had separated out from your lecture a little bit differently just because there's an additional thing that happens. But it starts the same way. You take your pi bond, which is your nucleophile, and you take a hydrogen away from the hydronium ion. And you're going to end up with a positive charge on your molecule, very much like what we did before. Now, the other alternative of where this goes is if we put the hydrogen here, and we've already discussed with alkenes why this is not such a great idea. It's the same idea that happens, that the stabilization, this is a less stable, not that a plus charge on a double bond is stable anyway, but this is less stable because no hyperconjugation, which is a type of induction. So it's not so helpful. So let us go ahead and then draw our next step. So we have a cation, and our water can attack that carbon. So I'm just drawing the hydrogen in so that we mark where it is. After a while, again, as you feel comfortable, you don't necessarily have to draw it in. So I have that, and hydronium, the oxonium ions are, again, not terribly stable. So if you don't want them to come off, we protonate. And now we have formed this enol. Now, enols are unstable, and very few of them have been able to be captured in nature, so we can use spectroscopy techniques and things like that to monitor how this is working and why it's working. And it's actually, we can use deuterated water or deuterated acid that could actually help us figure out what's going on here. Sometimes it's the mechanistic ideas of how the product must have been forming. Now, there's a couple of ways that this can happen, but because we're in acidic media, the most likely way is that acid is going to help us do this mechanism. Now there's an internal way that this does this, but because we have an acid catalyzed way, we have this enol, and we're going to get an acid catalyzed tautomerization. Like I said, if there was no acid there, it might be a little bit different, though very slow. So we pick up our hydrogen, our extra hydrogen, right? And remember, there's already other hydrogens there. I'm just showing you that we picked up that hydrogen, but there are 2 other hydrogens already present there. But we formed something that can undergo resonance because the OH here, and we've seen this before in chapter 3 of Klein's textbook. So we end up with this species, and again, we have a hydrogen here. I'm going to stop drawing it shortly. And we put the brackets around for resonance. Don't put the double dagger. Double dagger indicates that you're talking about a transition state. We're talking about resonance. Do not put brackets around mechanistic things. A lot of times people do that in class when they're learning. So the square brackets are for resonance. The square brackets around one thing is with the double dagger is transition state. So here we're talking about resonance, and this is resonance stabilized. Since this has is not a full octet, it's less stable, whereas this is more stable. So it's going to form, and as such, now this looks pretty much like our ketone. So our last step is to deprotonate. And we get a ketone. So that is how our hydration of alkynes work. Now, if I had a symmetrical ketone, we're actually going to end up with a couple of products depending on, if I have 2 alkyl groups on either side. So in that same process, I can either have my OH here added, or my OH can be added here. So I'm going to draw both. This is not a mechanism at this point, but if my OH added, I'm going to say A or B. So A and B. If my OH added in position A, when this tautomerizes, my ketone is going to be in that position. If I do B, wherever your OH is, you're going to tautomerize. So you're going to end up with 2 products. So to remember how to do this, my little trick is wherever your double bond is and your OH is, this is my trick for you, is to first start with that, then take your oxygen where take your double bond, and then you're going to erase it. And then put the double bond back over here. Okay, so you're going to move that around, and then you erase the oxygen. This is not a mechanism, but that is what I would do. So 1, erase pi. 2, make pi between carbon and oxygen. And 3, erase oxygen. So that's my trick, and you can use that for the other mechanisms. All right, we will have another video with the other mechanism.